So hello everyone, I'm recording the fifth video of this series, which will be about doping and ion implantation. So this will probably be a pretty long video, so I hope you all will take something out of it, that you have some learning points that you can learn out of it. So let's begin. So for doping a junction, right, remember that when we actually synthesize a MOSFET device, we need to often dope certain like junctions in our MOSFET, for example the source, the drain, sometimes the well in which the source and drain is created as well. And so normally these types of doping occurs in a two-step process. So the first step is basically either a pre-deposition or implantation, basically to get the dopant atoms inside the material, right? So by certain methods you get it inside the material, and often the second step is what we call a drive in, or sometimes it's called an anneal. But basically the point of this is to drive the dopants deeper in the material sometimes, and but more importantly is to activate the dopants to make sure that these dopants sit in its substitutional sites and is able to play an electrically active role. And so these are the two steps that generally have to keep in mind that we conduct when we do let's say a situation of doping. And so yep, as what I said, there's two steps. So the first step for introducing dopants, there are a few different ways. So for example, we can diffuse the dopants in from like a gas phase mixture that contains is rich in the atoms of the dopants they want to put in. And the second is a diffusion from a thin film of a solid. So now sometimes we layer down solid material on a silicon that contains the dopant atoms that you want to diffuse into the into the silicon. And so these two methods are generally called diffusion methods. And the third way, which is actually more common nowadays, is ion implantation. So it involves it's the second picture over here. It involves accelerating high velocity dopant ions that penetrate and implant themselves into the silicon material itself. And the last way, which is grown-in dopants, is actually quite common in nowadays the advanced semiconductor technology nodes, especially you have your FinFET architecture. Yeah, it is quite widely known that grown-in like doping is a method used quite commonly to dope certain areas of the FinFET kind of architecture. And so for the second step, right, redistributing dopants, right, normally we use it, we do it using a furnace, either that or sometimes, as I explain later, we need rapid annealing, and we use a rapid thermal annealing setup, which normally consists of a heating by certain halogen lamps. So okay, we'll cover that later on. So let's take a look at the pre-deposition method. So these first two methods, which involves diffusion of the dopants into the material. So it's not diffusion of the dopants that is already within the material, but diffusion as a method to get the dopants inside the material in the first place, right? These methods are sometimes called pre-deposition method because you're like depositing it first, right, as a preliminary step before we drive in the dopants into the material. So pre-deposition method, I'll just use that term to refer to it here. So normally it is done in a furnace process similar to thermal oxidation. Just that in this case your gases is not your oxygen or hydrogen or steam anymore, but gases that contain the dopant atom. So for example, you want to dope boron in, so we have B2H6, or we want to dope phosphorus in, then we have phosphine, right, PH3, right. So normally it's also mixed with other diluent gases, right, that are somewhat inert in a certain environment and is delivered to the wafer. However, as mentioned before, we can also do the diffusion from the thin film. So you can pre-deposit the thin film first that's rich in the dopant atoms. So examples include like these solid oxides of boron, phosphorus, arsenic. But it can also be, let's say, a liquid layer, right, POCl3 or BBr3, right. And so normally we conduct this pre-deposition method at the limit of solid solubility at the interface. So basically there's a certain solubility limit of any gas or like atoms within the silicon material, right. So there's a solubility limit. So it's just like, let's say your solubility limit of salt in water at a certain temperature, right. There's a certain amount of salt after which you cannot dissolve any more into the water. So same thing here, there's a solubility limit, right. Something called a solid solubility limit because you're dissolving it in a solid, which is silicon, right. So there's a solid solubility limit of various dopants within silicon, and normally we conduct this pre-deposition step at that solubility limit. So the reason for this is so that the concentration doesn't vary so much. So why do I say that? That is because if we, let's say, conduct the pre-deposition method below the solubility limit. That means if the concentration of your dopant gas or your dopant liquid or whatever varies, or the flow of it varies, for example, um, then the result is that the dopant uh, concentration that eventually enters the silicon wafer becomes unpredictable, because it depends on the rate of your flow of your, like say, dopant gases, your concentration fluctuation of your dopant gases. However, if you conduct it at the solid solubility, then even if, let's say, your dopant concentration, dopant gas concentration increases beyond that of the solid solubility limit, it wouldn't affect the amount of the dopants that eventually enter your silicon, right? Analogously, right, if let's say my water is already saturated with salt, even if I add in more salt, it wouldn't change the amount of salt that dissolves in the aqueous phase, right? So likewise, as such, so that's the reasoning behind why we often conduct our pre-deposition of the gases, right, of the dopant gases above, right, actually, to be more precisely, above, at or above the solubility limit in silicon. And so how do we actually mathematically model the, let's say, the diffusion of dopant atoms within the material? So we can consider the case of like a fixed dose that's applied. So in certain cases, right, normally for like ion implantation you see this more often, but basically for certain cases, sometimes we can deposit what we call fixed dose at basically at the position, let's say x equals to 0, for example, a fixed dose of dopants. And so we call this a delta function, because a delta function has a fixed integral. It has a fixed integral at a certain specified fixed x position. And so we can prove that if we diffuse, right, this fixed dose of dopants to the left and to the right of the material, right, the solution that satisfies fixed laws of diffusion, which is like certain mathematical laws that govern the diffusion process, right, we obtain this result. That means the concentration profile of the dopants that is diffused throughout the material follows that of a Gaussian profile. So this is like the same kind of profile as your normal distribution, also known as a Gaussian distribution. So we can see that the maximum, the peak, is this value, and is basically the concentration at x equals to 0 at a certain time t. So it's basically, this expression is a function of t. So what does it mean when it is a function of t? That means that the peak concentration, as you can see from this expression, right, decreases as t increases according to this relationship. And the diffusion distance, right, which is how spread out it is, it also increases as t increases according to this mathematical relationship. And one thing interesting is that the integral of a Gaussian function, of a standard normal function, for example, is 1. But since we multiply it by q over here, the total integral area below the curve is equals to q. And what this means is that because the area under a concentration distance graph is the dose of dopants you're adding in, what this simply means is that the total dose that's implanted into the material, that is diffused through the material, remains constant, which makes sense, right? Because in the ideal case, when we put a dose in the material and you diffuse the dose out, the dose by right shouldn't disappear and shouldn't increase, right? It should remain constant. However, there's a bit of a problem, because normally doping happens at the surface, right? Not somewhere in the middle where you can diffuse on both sides. Normally it happens at the surface, and diffusion occurs in one direction only. In this case, we basically do a reflected like Gaussian or one-sided Gaussian, where effectively we just multiply it by 2, right? Multiply by 2, so there's a 2 in the denominator over here, it disappears here, and the function is defined only for x greater than 0, for positive values of x. So we change basically the domain of the function, and we multiply the pre-exponential term by 2. Okay, so it's basically, you can think of it as the Gaussian distribution, but only limited to exist in the positive x direction, but maintaining the overall total dose at a constant of q. So you have to multiply by 2. However, that's not the only mathematical model of how the diffusion of, let's say, a dose of dopants can occur in the material. So another model is the infinite medium diffusion. So in this model is a fixed dose diffusion. We put a fixed dose of q, but this doesn't model all the cases, right? For example, in many cases we saw earlier, we have a diffusion from a thin film, right? So we put, let's say, a gas of film of dopants, and we diffuse the dopants from the film into the silicon. And so if the film is thick enough and concentrated enough, this can be thought of as effectively an infinite source of dopant atoms. So it's no longer a fixed dose of dopant atoms that you see over here. It's an infinite source, heavily doped infinite source, infinite medium of dopant atoms. And so in this case, if we apply this kind of starting conditions and apply fixed law of like diffusion, we will obtain a different solution to the to the profile of the dopant atoms, right, after diffusion. And so this is what we call ERFC, or a basically complementary error function. So a complementary error function is basically, you can think of it as a mathematical function. However, we cannot easily like take the inverse of this function. So in order to, let's say, calculate oftentimes your values of x or d or t, you have to consult an error function table, a bit similar to how we often consult like statistical distribution tables for like Gaussian distribution, log normal distribution, things like that. So likewise, we also have to consult a distribution table to solve the complementary error function. Okay, so the unique things about this function that's very important is that the dose at x equals to 0 always remain constant. It's always half of the dose at the infinite source. Okay, and the dose beyond basically x equals to 0 continues to increase with the annealing time t. Right? And so, however, most of the time we aren't interested, right? So over here, right, this part of the curve is still within the film. It's still within the film that's rich with dopants, right? However, we are only interested in the part that's in the silicon, which is this part of the curve. So if we cut off the curve here and just look at this portion, we can basically just modify this equation. Instead of your C over 2 is this point, instead of calling it C over 2, we call it CS, surface concentration, and the rest of the function remains the same. We call this CS, surface concentration. And so we can obtain this expression, this modified expression for the dopant concentration over distance within the material at a certain time of annealing T. And so we can find the dose by integrating the error function, and it turns out the error function is defined in terms of let's say a differential. So we can basically get a closed form solution of the integral of a complementary error function, and so we obtain this expression for the dose. So we can see that the dose that enters into the material is not a constant but increases with time. So this is different from this case where we have a fixed dose, and no matter how long you anneal or diffuse, right, the dose remains constant in the material. However, in this case, right, the film acts as a infinite source of dopant. So it makes sense that the longer you diffuse, the more dopant atoms can move from this infinite film into your silicon, and therefore the greater the dose. Therefore, dose increases as temperature increases. Okay, so in both of these models, we see this D here. Okay, you see this D. This one D as well. So for those who have studied material science before, you should know that this D stands for diffusivity, also known as the diffusion coefficient, and that you should know that it follows an Arrhenius relationship dependence on temperature. So basically, not only does it depend on temperature, it depends also on the activation energy of diffusion. Okay? Activation energy. And so obviously it will then differ based on your dopant atoms that is diffusing, right? Different dopant atoms should have different activation energy or diffusion, right? And therefore should have different diffusivity at a certain temperature. So we can consider what is known as intrinsic diffusion, which is calculating the diffusion coefficient of dopant atoms assuming that the silicon material is approximately intrinsic in nature. That means it's approximately undoped. Okay? So, however, while this may seem like a bad assumption, it turns out that the intrinsic carrier concentration of silicon is very large at the process temperatures that we're dealing with, which is like higher temperature, 1000 degrees Celsius. So, this intrinsic silicon assumption somehow still holds. So, do we want slow or fast diffusers, right? Obviously, as technology node progresses, we want smaller and smaller transistors with thinner and shallower regions being defined. So we don't want fast diffusers. They will diffuse too fast and cause all sorts of problems when dealing with transistors of that minuscule size. We want slow diffusers as much as possible. So for the n-type, right, doping. So for n-type doping, we often use the arsenic because arsenic is a slow moving dopant, and at the same time it also has a high solubility in silicon. However, for the p-type doping, unfortunately we see that boron is the only one with high enough solubility to be widely used in IC manufacturing. Okay? So even though B is a fast diffuser, right, boron is a fast diffuser. However, it's the only one with high enough solubility for us to use it commonly in the fabrication of transistors. So now I'll briefly cover some non-ideal diffusion effects when diffusion deviates from ideality. So the first case is field enhanced diffusion. So this basically is the effect of an electric field that is spontaneously formed in the material. So how is it formed? Right, it's formed when electrons and holes diffuse faster with temperature compared to the dopant ions, because electrons and holes have a smaller effective mass compared to ions. Ions are much heavier, right, than electrons, for example. So electrons actually end up moving, diffusing faster than the ions, and this creates an electric field, right? We have a negative charge here, we have a positive charge here. There's an electric field. There's an electric field that's pointing outwards, and this accelerates the movement of the positively charged ions. So this is a field enhanced diffusion, and basically this field enhances the rate of diffusion of the dopant atoms. The second point where diffusion can deviate from our ideal cases that we've been discussing is extrinsic diffusion. So as mentioned earlier, oftentimes when you talk about diffusivity, right, the diffusion coefficients, we consider the case of intrinsic diffusion in intrinsic silicon. However, when the doping concentration is much higher than the intrinsic carrier concentration Ni, there becomes is a much more significant deviation of the diffusion coefficients from the ideal case in the intrinsic case. So this effect on diffusion is an enhancement kind of effect. So basically diffusion is faster in extrinsic diffusion in regions where there's a higher dopant concentration. This is because having a higher dopant concentration means there are a greater concentration of dopant atoms which have different size from that of silicon atoms. So having different size from silicon atoms, these dopant atoms will distort the silicon lattice and create defects. And with a higher defect density, defect always enhances dopant diffusion. Right? Defect always enhances dopant diffusion. Why is this? So this is because many diffusion pathway of dopants happen along defects. For example, if you have a vacancy, a dopant atom can jump into it. If you have an interstitial, the dopant atom can jump out of the lattice and be replaced by the interstitial, and the dopant atom is now in the interstitial region and can diffuse, right? So diffusion is often driven by defects, and so if there's an increase in the defect density, there will certainly be an increase in diffusion. So the effect is that now your diffusion coefficient is a function of your doping concentration, right? It's a function of your doping concentration. So you can have like basically an expansion series where you can have like terms that are dependent on doping concentration, dependent on the doping concentration squared, and things so on and so forth. And by considering these terms, right, we realize that the profile of the diffusion of the dopants deviates from that of the ideal case where we only consider a concentration independent diffusion coefficient. And another point that I'm going to cover is actually a point that I did cover in the previous video, I think, which is segregation and interfacial pileup. So this is often the case when you have a layer of oxide or any other, like let's say non-silicon material, some dielectric for example, on the silicon surface. So your dopant atoms, your arsenic, your phosphorus, your boron, they may have a different preference, a different selectivity for your oxide versus your silicon. So for example, boron really prefers to be in your silicon dioxide. So there's a downward trend near the oxide interface. Whereas phosphorus and arsenic really have a preference for your silicon. So there's an upwards trend near the oxide interface. So we call this outward strand, for example, interfacial pileup. So that will certainly affect your dopant concentration near the interface, and especially given that how many of the junctions in the transistor, in the MOSFET, is covered by a layer of oxide, right? So this actually makes it a bit challenging, let's say, sometimes to have a ideal dopant profile that we want according to our design plans. So now I will also talk about oxidation enhanced and oxidation retarded diffusion. So oxidation, right, is basically a process that introduces compressive stress on the silicon, as I mentioned earlier. Why compressive stress? This is because the oxide lattice is bigger than the silicon lattice below, and so it compresses the silicon lattice below. And so what happens is that this results in basically the formation of interstitials, because if you compress the silicon, some silicon atoms will pop out of the lattice and become interstitials. And so when we have things like boron and phosphorus atoms that prefer to diffuse with interstitials, that means the presence of silicon interstitials enhance this boron and phosphorus diffusion. Then we have what we call oxidation enhanced diffusion. So why is boron and phosphorus prefer to diffuse with interstitial? This is because they are light atoms. They like to be in the diffusing along the interstitial pathway between the silicon atoms. Okay, and so when we have silicon interstitials, they can undergo a replacement in their positions with your boron atoms, for example. So a boron that was in the substitutional site pops out into the interstitial, and interstitial silicon goes in. And so now your boron is in the interstitial site. And so a boron in the interstitial site can move along the interstitial spaces and diffuse along your material. However, when you have bigger atoms like antimony, right, antimony cannot very easily diffuse along interstitial positions. So it prefers to diffuse with vacancies. How this works is that there's a vacancy, the antimony atom jumps into the vacancy, then it finds another vacancy to jump into, so on and so forth. So we have what we have. We have what we call oxidation retarded diffusion for antimony. However, when we actually grow a nitride layer instead of an oxide layer, right, the nitride layer introduces tensile stress onto the silicon. So when you are subjecting the silicon layer to tensile stress, that means you are like pulling the silicon layer, right, certain vacancies pop up, right, certain vacancies appear. And so these vacancies, right, we call it a vacancy injection. And so this causes the opposite effect. So now instead antimony is enhanced and boron and phosphorus is retarded, right? So we have the opposite effect when it comes to nitridation. Okay, so now I've covered a bit on diffusion. So now for the next section, I'll focus much more on ion implantation. Okay, so how does ion implantation work? Okay, I'll cover later, but for now just know that ion implantation is currently the dominant doping method. So why is it the dominant doping method? Let's look at the pros and cons of ion implantation versus what we call the pre-deposition, right, the solid or gas phase diffusion. Okay, so the pros of ion implantation is that normally you can use a room temperature mask because ion implantation doesn't need heating itself, right? The annealing step after that requires it, but not the implantation itself. We can have very precise dose control by controlling the amount of ions that enter the silicon. And we can have very accurate depth control by controlling the energy of the ions that enter into the silicon, right? However, what are its cons, right? Ions are energetic species when they enter into the silicon at high velocities. So it tends to cause implantation damage, which can cause problems like amorphization and enhanced diffusion. At the same time, right, it can also introduce other kinds of lattice defects like dislocations, which can cause leakage in the device. And also there's this thing that we need to consider, which is implant channeling, which is an additional point to consider as it can affect your dopant profile. And then let's look at the other case of solid or gas phase diffusion. So the pros is that there's no damage caused by doping, and that basically it can be fabricated in larger batches. You can have like a few wafers and then we diffuse together, right? We diffuse the gases in together. However, the cons is that, as mentioned earlier, the diffusion is limited to the solid solubility level. So we cannot modify the concentration of the gas phase in order to effect a difference in the dopant concentration. It's a bit hard for us to do that. Okay. At the same time, it's also hard to achieve a low surface concentration without a long drive in. without a long driving, because we are limited to diffusing in dopants at the solid solubility level, which is pretty high. So if we want, however, the surface to have a low concentration of dopants, we need to drive the dopants in a lot, right? And that takes a long while, and that's not good because it gets a very deep junction in the end of the day. And so as a result of all these factors, depositing a low dose becomes very difficult. So as a result, ion implantation is now the default and the most commonly used method for doping silicon to make field effect transistors. So these are some of the advantages they've already mentioned, right? Large range of doses can be used, accurate dose control, right? Low temperature process, which results in a wide choice of masking materials being available, and we can also achieve buried profiles. So we can, let's say, choose to implant most of our ions at a certain depth within the lattice instead of at the silicon surface. And we can do that by, let's say, having a more energetic implant. So ion implantation also requires two stages, because oftentimes when we implant it, right, the lattice is damaged. We need an anneal step. The anneal step not only heals the lattice, but also ensures that your dopant atoms occupy the substitutional sites and therefore are electrically active. Oops. So the equipment normally used for ion implantation, right, involves an ion source that converts molecules into ions. These ions are then discriminated based on their mass to charge ratio by analyzing magnet. Then they are accelerated through electric field, right? There's a mechanism in which the ions that are not charged, rather atoms, right? Atoms, right? Not ions, right? Atoms are trapped, and those ions that are charged at a high velocity are then directed to the wafer. The wafer is often connected to a electrical device called Faraday cup, which can measure the charge accumulating on the wafer, and that is a way to measure the amount of dose, the ion dose that's implanted into the wafer. And so that's how we monitor the process of ion implantation. So the distribution of implanted ions can often be modeled by a Gaussian distribution also. So in this case, we have two parameters that's important. One is your RP. Your RP is basically your projected range, so is the maximum of your Gaussian profile, and that is taken to be the range of the ion implantation process. So if you have a more energetic implant, right, your range is deeper in, your peak of the Gaussian profile is deeper in the material, right? And you also have this delta RP. Delta RP is like the standard deviation of the distribution of the implantation as a standard deviation. So these two factors are important because it determines how deep you implant the ions, that's RP, and how broadly the ions spread in the material during implantation, which is delta RP. So this is before any annealing or diffusion. It's purely from the implantation process only. And so likewise, you can also take the total dose by integrating the implantation profile. So of course, the kind of ion that we use, right, affects the implantation distribution. So the lighter your ion, right, the deeper your ion can penetrate inside the material because it is lighter and moving faster, right? So the further they can travel in. And of course, the higher your voltage, the deeper your ions will be implanted. Then how about delta RP? How about the standard deviation or the spread of your implantation distribution? Turns out it also varies the same way, right? That means as your ion gets lighter, right, your delta RP gets larger. As your voltage, your energy gets higher, your accelerating voltage gets higher, your delta RP also gets higher. And so the reason behind this is that because the deeper the ions travel in the material, so the greater your RP, the more scattering these ions can undergo as they penetrate deep in the material, and hence the larger the standard deviation. So there's a correlation between your RP and your delta RP, positive correlation. However, often case the perfectly symmetric Gaussian profile is not the case. We tend to have asymmetric profiles. So light ions tend to be backscattered. So for example, boron is skewed towards a shallower region, as light ions tend to hit the silicon atoms and scatter back, right, in the somewhat of an elastic collision, right, scattered back from the silicon ions. However, when you have heavy ions, right, like antimony, they are scattered forward. So they hit the same silicon atoms, but because they are not so light, they are not scattered back, but instead they are still scattered forward. And so we have a forward scatter of a forward skewed kind of profile instead. So actually a more accurate distribution is a Pearson distribution, but for future slides we'll still show the Gaussian distribution because it's a simpler model that's more easily visualized. So remember, ion implantation requires two stages. Implant, that has been discussed. Now we'll look at anneal. Okay, we'll look at anneal. So remember what we covered some minutes ago about how when you have a fixed dose, right, and diffuse the fixed dose, right, the resultant profile follows a Gaussian distribution. Okay, follows a Gaussian distribution. So we use this concept right now. Okay, so how do we model rather the implantation and anneal profile after anneal has happened, after annealing has happened? How do we model that profile? So let's consider the first case where we have a shallow implant. So the red color curve is the distribution of dopants immediately after implant. So we see it's very narrow and it's approximately at x equals to 0. So we can consider this equivalent or approximately equivalent to a delta function. A delta function is a very narrow function at x equals to 0 with a fixed dose. In this case, it's a very narrow function at x equals to 0. And we know it's a fixed dose because the ion implantation step has finished. There's no more adding more dopant atoms. So the dose is fixed already. The dose is fixed by the red curve. So we can use this eventual equation as our equation over here to describe the profile after annealing. So we approximate the red curve to be a delta distribution. We know that there's a fixed dose. We utilize the result that we have shown earlier to describe the doping profile after annealing. So it's a one-sided Gaussian distribution. Okay, so in this case, right, of course we can approximate that to be x equals to 0, right? However, right, it's also possible, for example, for us to consider the case where x is non-zero, right? X is non-zero, so you can x that at 0.4. So the resultant Gaussian profile, for example, will still be Gaussian. However, it will not be a perfect one-sided Gaussian, right? It will not be a perfect one-sided Gaussian, but it's a Gaussian that is reflected somewhere to the left of its peak. Okay, but that's slightly more complicated, but likewise we can also do the necessary mathematics to obtain it. So how about the second case where we have a deep implant? So the x is nowhere near the interface, and at the same time there's a broad distribution after ion implantation. Right, there's a broad distribution after ion implantation. So we cannot approximate a delta function anymore because one of the assumptions, which is a very narrow distribution, right, it doesn't hold over here. Right, it doesn't hold. It's a broad distribution. So we need to effectively take a Gaussian function and then diffuse it. So we can show that mathematically the result is a convolution of two Gaussian functions, which is simply like an expression over here. So we see that now the peak of the diffused and annealed profile, which is the green profile, is still at your RP, still at your projected range of the implantation step. However, now the spread of the distribution has two terms: your delta RP, which came from the implantation step, and now your dt, your 2dt, which came from the annealing step, where your t here is the time of anneal. Okay, so this is just for you to know lah. You may not really need to actually use these mathematical equations. So now I'll cover a few more things about the ion implantation step. So you can put anneal aside for now. Let's talk about the ion implantation step. Because remember, the ion implantation step is a highly energetic step. These ions are high in energy. They cause damage. They cause problems. So now we'll see what are these problems and damage that can arise. So first, let's talk about channeling effect. So the silicon lattice is basically the same kind of lattice as your diamond lattice, right? So certain FCC kind of lattice. And the unique feature of this lattice is that in the 110 direction, if you look at the lattice in the 110 direction, we see these channels. So these are empty channels that are wide and they are straight and it allows your ions to go through it, just like the bullet train going through a tunnel, right? And so the problem is that when your 110 phase is exposed to your ion implantation, right, ion implantation exactly along the 110 direction, the channeling effect can be very severe and will cause your dopants to basically drive very deep into the material. Take a look at the red line over here, where your tilt is 0 degrees. That means it's exactly aligned with your 110 direction. Okay, compared to your amorphous case, where there's no channels, right? Amorphous silicon has no channels, so your black color things, your black color curve, right? It is much deeper in. So how we can mitigate this is just by, for example, tilting the wafer. So when you tilt the wafer, right, the ions are no longer perfectly aligned with your 110 channels. So by increasing your angle of tilt, you can make your implantation kind of depth, right, less and less, smaller and smaller, right? But another way, perhaps more effectively, is this idea of pre-amorphization. So what we do is that we add a high dose silicon implant. So this implanting silicon in silicon doesn't make much sense, right? Because this is not to actually achieve any doping. It's to just mess up your silicon lattice, to mess it up, to cause it to amorphize, to be amorphized. And so what happens when your lattice is amorphous? Right, there's no more channels, right? Because there's no more like fixed lattice kind of arrangement, right? So alternatively, you can also add a thin layer of oxide on the silicon surface, because silicon dioxide, when grown on silicon, is always amorphous. So, but either ways, this kind of amorphization helps to stop the channel effect, and so your depth of your dopant penetration becomes much smaller. Okay. So now I'll cover the ways in which these dopant ions are stopped in the material. We learned that these dopant ions will eventually stop, right? That's why there's a projected range and there's a standard deviation of your projected range. However, how are these ions stopped? There's two main mechanisms, right? Nuclear stopping, that's when your ions like hit your nuclei, the silicon nuclei, again and again and again until it loses the energy, right? That's how it loses energy, and that's called nuclear stopping. Another way in which the ions can lose energy is for electronic stopping, which is interaction with the electrons. So there can be two ways, right? Firstly, when the ion is moving through the electric field of the electron clouds, there's a polarization that's induced in these electron clouds that creates a retarding electric field that drags down the ion. So you can think of this as somewhat like a fast car driving through air, right? F1 car driving through air, right? Air resistance slows the car down. Likewise, the ion traveling through the electron cloud, a resistance from this electron cloud slows the ion down. Another way is directly colliding with electrons, obviously, and then losing momentum. So the thing about electronic stopping is that it's directly proportional to ion velocity. Like the F1 car, air resistance is proportional to the car velocity, right? So likewise, right, the electronic stopping, the energy lost in electronic stopping mechanisms are directly proportional to the ion velocity. So let's take a look at certain ions, right, like your arsenic, your phosphorus, and all that. Okay. So your red color curve is the energy lost to nuclear stopping. Your blue color curve is the energy lost to electronic stopping. So nuclear stopping is more important at lower energies, and then it declines at higher energies, right? And we see that it's more significant for your arsenic, right? It's more significant for your arsenic than your phosphorus, than your boron. So it's more significant for your higher energy, higher mass ions. It's more significant for your ions of higher mass. And so this makes more sense, right? Because when the ions are of high mass, right, when they collide with the silicon atoms, they tend to lose energy faster. Okay. However, we see that electronic stopping is something that's relatively independent of the ion, right? So these straight lines are relatively close together. So the conclusion for this is that nuclear stopping, right, becomes more significant at lower energies. Electronic stopping becomes more significant at higher energies. Which one, nuclear stopping or electronic stopping, causes the damage to the lattice? Obviously, it's nuclear stopping, because it's only when you collide with the nuclei of the silicon do you disrupt and destroy the silicon lattice, right? So the conclusion for this is that for light ions, damage to the silicon lattice only occurs near the end of their path where they are low in energy. Take a look at boron curve. At high energy, most of boron stopping arises from electronic stopping, but at low energy, right, the nuclear stopping interactions are more significant for boron. So for light ions like boron, they interact with the silicon nuclei more to a greater extent when they're lower in energy. And when are these boron ions lowest in energy? Is when they are near the end of their path, that they have made through the silicon lattice, right? However, we see that for heavy ions, right, nuclear stopping is very significant for all energy values. So that means that heavy ions will produce this kind of damage to the silicon lattice along the entire path, regardless of their energy, right? Regardless of their energy. So this is just something to take note. Right? So what is the result of um, your damage to the lattice? The result of the damage to the lattice is that there needs to be a damage annealing step. So for low dose implant, right, the recombination of the interstitials and vacancies that are generated from the damage to the lattice happens very quickly, therefore healing the crystal damage. However, we need to remember something. When we, let's say, implant your dopant ions into the silicon materials, we create interstitials and vacancies as a result of damage to the silicon lattice. But at the same time, we also add in dopant atoms, right? So let's say we send in 30 dopant atoms, it creates 100 interstitials, which creates 100 vacancies. So some of your vacancies, 70 of your vacancies, will combine with your interstitials. However, the other 30 of your vacancies will take up your 30 of your dopant atoms. So what happens is that we have some remaining interstitials left behind that it does not combine, is not able to combine with a vacancy to anneal. So these interstitials remain floating around. So these are called +1 interstitials. Okay. So why are +1 interstitials important? This is because +1 interstitials, they don't just float around indefinitely. They tend to group together in the 3-1-1 direction. So if we use a transmission electron microscope and like image the silicon with a certain zone axis that allows for the capturing of these 3-1-1 direction defects, you will see these defects appear on the TEM image. Right? So these defects are also called 3-1-1 defects, right, due to their direction, and these play the main role behind transient enhanced diffusion, which we'll see later. However, in addition to, let's say, just generating your interstitials and vacancies, so in this case, right, interstitials and vacancies are generated in the silicon lattice, right? However, we assume that the general silicon lattice remains more or less preserved. However, if your ions that you're implanting are of high enough energy or large enough dose, there's a high possibility of complete amorphization of the silicon lattice. So the crystal is completely amorphized, right? So we can see this in these TM images where there's a clear distinction between the layer of silicon that remains crystalline and the layer that's already become amorphous due to the ions that are implanted in. So it is easier to form the amorphous layer when ions are implanted at a lower temperature, because then your silicon atoms have less energy to rearrange themselves into the ultimately thermodynamically more stable crystalline configuration. So what happens with this amorphized silicon? Actually, you do not have to worry, right? Because there's something called solid phase epitaxy can happen. So it's actually a rapid layer by layer crystal regrowth in the amorphized region, where the crystal rearranges itself back into the crystalline state in the amorphized region. And this can happen at relatively low temperature, so it's not too much of a concern. And so actually, in the amorphized region, right, there are no more +1 interstitial because the whole lattice is broken down and regrown. So if there's any like extra atoms, right, caused from the addition of the dopant atoms, they are able to rearrange into the newly grown silicon lattice. So there are no +1 interstitials, no such problem, right? However, there's still another kind of problem, which is what we call the end of range dislocation loops that occur at the interface between the regrown, formerly amorphous regrown epitaxial layer and the original crystal lattice below it. Okay. So as a summary, right, if like ion implantation occurs below the amorphization threshold, that means the lattice is still not completely amorphized. There's just creation of interstitials and vacancies due to ion damage, right? We create +1 interstitials throughout the area that's been exposed to the ion dose. However, if we implant an ion dose high enough to cause amorphization, the amorphized area that eventually undergoes solid phase epitaxy, right, will not have your +1 interstitial. However, your +1 interstitial will still happen in areas of the silicon exposed to the ion dose, but not high enough to have undergone amorphization. So the good thing is that when we anneal the damage, when we anneal such that solid phase epitaxy happens, for example, the dopants are often, almost always, right, able to find its way to sit in the substitutional sites to be able to be electrically active, right, to be able to be electrically active. Okay, now to talk about transient enhanced diffusion. So this is caused by the 311 defects that I mentioned earlier. So when, right, let's say we want to anneal the material, uh, let's say we want to anneal the material to be able to get a better distribution on dopant atoms, but your 311 defects are still there. What happens, right? Right. What happens is that these 311 defects, right, actually undergo a dissolution process, and when these 311 defects dissolve, they release the interstitials, right? So these 311 defects are ultimately composed of interstitials, and when these 311 defects dissolve, they provide a source of interstitials which will accelerate the diffusion of the dopants in your material. So you can do an experiment. For example, we know that the dt, which is basically like a constant that defines how fast your diffusion of the dopants occurs. So dt at 1000 degrees Celsius by right should be greater than dt at 800 degrees Celsius. However, we realize that the lower temperature process gives a deeper diffusion. Why? Because at this lower temperature, right, the 311 defects, which are source of interstitial, can stay longer and continue releasing the interstitials over this longer period of time, therefore enhancing the diffusion over a longer period of time. So at the end of the day, actually 800 degrees Celsius anneal, right, results in a deeper diffusion drive in compared to 1000 degrees Celsius, which is against what we would expect. Okay. So this is actually an important factor to consider for today's day and age, because now we want like very shallow junctions, for example. However, this transient enhanced diffusion will result in like the junction depth being larger, the diffusion depth being larger than what we expect. So how do we solve this, right? We use rapid thermal anneal. So we basically do your annealing step at a much higher temperature, but at a much shorter time. And the reason for this is because at higher temperatures, transiently enhanced diffusion, right, lasts for a very much shorter period of time. Your 311 defects last for a very much shorter period of time before disappearing at a higher temperature. So we need to use higher temperatures to anneal. But of course, if we ramp temperature up, right, to achieve the shallow doping, we need to shift your time period smaller, right? So the solution to this is rapid thermal anneal. So as you can see, this is what is done, right? So during the period where your 311 defects still exist, right, we have a high rate of diffusion. So this high red line represents transiently enhanced diffusion of your dopants, right? It represents transiently enhanced diffusion of your dopants. However, once these 311 defects run out, right, the diffusion goes back to its normal level. So what RTA does is that it shrinks this part. It shrinks this rectangle to a shorter period of time. So if, right, in a short period of time we consume all the 311 defects by the use of a higher temperature applied over a short duration, right, this enhanced diffusion only occurs for a short period of time before diffusion goes back to its normal rate, right, normal rate of, let's say, 1, right. Okay. So how do we do rapid thermal annealing? We normally use a setup that consists of flash lamps, right? Usually it's some form of xenon lamp or some form of halogen lamp. And so these lamps are basically able to heat up to very high temperatures at very short durations. So this will heat up the wafer, right? This will heat up the wafer. Your halogen lamps and your flash lamps. So normally what is done is that the halogen lamps do a certain preheating, and then after that your flash lamps do the flash annealing. Okay. So the preheating step allows for your solid phase epitaxy and your basically your healing of any amorphized or any damaged region, and then your flash annealing, right, does your dopant drive in while minimizing transiently enhanced diffusion. So but the main problem with this is how to ensure uniformity, because we have different lamps over here, so it's no longer like a uniform thermal environment. We are relying on these lamps to provide your thermal energy, so it's important to ensure a uniformity across the wafer. Hey, so that's the end of this. I would say pretty long. I'm not sure how long I took, but probably pretty long video about doping and ion implantation. So in the next lecture, I'll cover etch, more specifically both wet etch and dry etch. So I think it's a very important topic that I'll be covering in the next video as well. So I think it's important that, yeah, you all also watch the video if you want to learn more about etch. Okay, so that's the end of this video, right? Hope you all found this engaging and insightful. Okay, and see you in the next video.